When physicists first studied black holes in detail, they noticed something unsettling. The amount of information a black hole can contain does not grow with its volume, but with the area of its surface. That single result quietly challenged how space itself is supposed to work. If information defines reality, then depth may not matter as much as boundaries. Tonight is less than #0. 5# is greater than we explore a possibility that has followed modern physics for decades, that everything we experience, distance, solidity, even gravity, may be encoded on a distant surface like a cosmic record written at the edge of the universe. From the smallest measurable length to the glow of the cosmic microwave background, researchers have kept running into the same pattern again and again. This story is built from equations that were tested, measurements that were taken, and discoveries that quietly changed how scientists understand space and time. It starts at the moment when this idea could no longer be set aside in part 1 is less than #0. 5# is greater than what if everything you've ever touched is just a projection from the edge of the universe. The first crack in our everyday picture of space did not come from telescopes peering across billions of kilometers, but from equations written to understand objects so dense that nothing escapes them is less than #0. 5# is greater than. When physicists studied black holes carefully in the early 1970s, they found something deeply unsettling. The amount of information associated with a black hole did not scale with how much space it enclosed. It scaled with the area of its surface. Not with depth, not with volume, with area. This result emerged from the work of Jacob Bekenstein, who asked how the second law of thermodynamics could survive in a universe that allows black holes to swallow matter, radiation, and everything carrying entropy. Bekenstein proposed that a black hole must itself have entropy, and that this entropy is proportional to the area of its event horizon. At first, the idea seemed almost decorative, a clever way to keep a cherished law intact. But in 1974, Stephen Hawking's calculations forced the issue into the open. Hawking showed that black holes are not truly black. They emit radiation, now known as Hawking radiation, with a temperature and entropy that match Bekenstein's formula precisely. The equation was simple. The implication was not. Black hole entropy increases with surface area measured in square meters, not with the cubic meters of space inside. A solar mass black hole has an event horizon only a few kilometers across, yet its entropy exceeds that of ordinary matter, occupying an enormous region of space. According to the math packing, more matter into the same region does not increase information without limit. At a certain point, nature enforces a boundary. This was not philosophical speculation. It followed from well-tested physics, quantum field theory, general relativity, and thermodynamics. The constants appearing in the formula include the speed of light, the gravitational constant, Planck's constant, and Boltzmann's constant. Every term was already known from laboratory experiments or astronomical observations. The surprise came from how they fit together. If information is physical, and if black holes represent the densest possible storage of information, then the maximum information content of any region is set by its boundary, is less than #0. 5# is greater than this. Idea slowly crystallized into what Gerard Hooft and Leonard Susskind later named the holographic principle. The name was chosen carefully. A hologram stores a 3-dimensional image on a 2-dimensional surface. Every part of the image is encoded non-locally on that surface. The analogy was not perfect, but it captured the core insight 3-dimensional physics might be fully described by degrees of freedom living on a lower dimensional boundary. This was not an abstract guess. It arose because black holes refuse to behave like ordinary objects. When matter falls past an event horizon, information appears to vanish from the outside universe. Yet quantum mechanics does not allow information to be destroyed. The tension between these principles became known as the black hole information problem. To preserve consistency, many researchers concluded that information must remain encoded on the horizon itself, even as the black hole evolves and emits radiation. Observations have not directly imaged this encoding, but modern astronomy has confirmed every piece of the framework surrounding it. The Event Horizon Telescope has resolved the shadow of the supermassive black hole at the center of the galaxy M87 and later Sagittarius A star, matching predictions of general relativity with remarkable precision. Xiaoyu Jinghao Ling 5# is greater than X-ray observatories, operated by NASA and ESA, have mapped accretion disks and relativistic jets, confirming how matter behaves near event horizons. None of these observations contradict the thermodynamic description of black holes. All of them reinforce it. The deeper consequence emerges when the black hole result is treated not as an exception but as a rule. If black holes represent the maximum possible entropy for a given region, then ordinary space must obey the same limit. Xiaoyu Jinghao Ling 5# is greater than node. This leads to a striking conclusion. The fundamental degrees of freedom describing reality scale with area, not volume, even when no black hole is present. At first glance, this conflicts with everyday experience. We live in a world where rooms have volume, where objects occupy space, where depth seems essential. But physics has often overturned intuition. In the early 20th century, atoms were revealed to be mostly empty space. Later, quantum mechanics showed that particles do not have definite positions until measured. The holographic principle suggests another step in this pattern. Space itself may not be fundamental. This shift did not arise from speculation about consciousness or perception. It came from attempts to make established theories agree with one another. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes matter and radiation in terms of probabilities and information. Black holes sit precisely at the intersection of these frameworks. When they are treated carefully, they force information to the foreground. Leonard Susskind summarized this tension bluntly. The world is not made of particles and fields as we once thought. It is made of information. The statement is often quoted, but it reflects a specific technical claim, not a metaphor. Information here refers to quantum states correlations and the limits imposed by Planck scale physics. The scale involved is extraordinarily small. The Planck length is about 1.6 times 10 to the power of minus 35 meters. When the area of a surface is measured in units of the Planck length squared, it gives a dimensionless count of how many independent bits of information can be stored. This count matches black hole entropy exactly. Xiaoyu Jinghao Ling 5# is greater than. No experiment has directly accessed this scale, but every indirect test of quantum field theory and gravity remains consistent with it. Observations of the cosmic microwave background by the Planck satellite show that the early universe was remarkably uniform, with tiny fluctuations at the level of 1 part in 100,000. These fluctuations encode information about the universe's initial conditions. When theorists attempt to model how much information could be packed into the early universe, they again encounter limits consistent with holographic bounds. Even the most advanced simulations of black hole mergers, now confirmed by gravitational wave detectors such as LIGO and Virgo, treat horizons as surfaces with well-defined properties. The gravitational waves detected from these events carry information about the masses, spins, and horizons of the merging black holes, is less than #0. 5# is greater than nothing in the data suggests that information is stored deep inside in a way that escapes the area law. None of this proves that the universe is literally a projection in the cinematic sense. Physics does not claim that space is fake or that objects lack substance. The claim is narrower and more precise. The claim is that the underlying description of reality may require fewer dimensions than it appears to have. What we experience as volume could emerge from relationships defined on boundaries. This perspective reshapes how gravity itself is viewed. If information lives on surfaces, then gravitational dynamics in the interior might reflect how that information is arranged. Gravity becomes less like a fundamental interaction and more like a large-scale effect of deeper bookkeeping rules. This idea remains under active investigation, but it is grounded in equations that already work where tested. Importantly, this framework does not depend on future technology or unverified instruments. It rests on results derived from black hole thermodynamics, confirmed astrophysical observations, and mathematical consistency between established theories. That is why it has remained central to research for more than 4 decades. What began as an attempt to rescue the second law of thermodynamics has quietly altered how physicists think about space entropy and reality itself. The edge of a black hole, once treated as a mathematical curiosity, became a testing ground for the deepest limits of nature. And from that edge, a broader picture started to take shape, one in which surfaces matter more than interiors. As this boundary-based picture continues to agree with both theory and observation, a more demanding implication comes into focus. If gravity and space can be described by information stored on a surface, then what we experience as depth may not be fundamental at all, but instead arise from processes taking place beyond our direct view. Present, structured, yet not immediately visible. And pas deux. Why does a black hole remember only its surface, not its inside? If an object falls into a black hole and disappears forever from view, what gives physics the confidence to say that the black hole still keeps its information, yet only on its surface, not deep inside? In modern physics, black holes are not mysterious because they are exotic, but because they force well-tested laws to coexist under extreme conditions. Is less than #0. 5# is greater than. On one side stands general relativity, a theory verified across a century of observations describing gravity as the geometry of space-time. On the other stands quantum mechanics, equally tested, governing information probabilities and the evolution of physical states. A black hole places these two frameworks into the same natural laboratory and demands internal consistency. This story begins not with wonder, but with discomfort. In the early 1970s, Jacob Bekenstein approached black holes from an unexpected direction: thermodynamics. The second law of thermodynamics states that entropy, a precise measure of microscopic disorder, tends to increase in closed systems. This law is not philosophical. It is confirmed in engines, radiation, chemical reactions, and every laboratory system tested. Bekenstein considered a troubling scenario. A box filled with hot gas carries entropy. If that box is dropped into a black hole, all of its contents vanish from the outside universe. If the entropy truly disappears, the second law is violated. To preserve the law, Bekenstein proposed a radical but logically constrained idea: a black hole must itself possess entropy. And that entropy cannot depend on the inaccessible interior. It must depend on the only physically meaningful feature available to an external observer: the event horizon. This was not initially welcomed as a discovery. It looked like a clever fix, but Bekenstein went further. He argued that there exists a fundamental upper limit to how much entropy, and therefore information, can be packed into a region of space. Once energy density exceeds that limit, gravity inevitably collapses the region into a black hole, enforcing a new accounting rule. From that point on, information content is controlled not by volume but by boundary area. The idea became unavoidable after Stephen Hawking's calculation in 1974. Hawking applied quantum field theory to spacetime near an event horizon, a region where gravity stretches time so severely that quantum effects cannot be ignored. In quantum physics, empty space is not truly empty. Even the lowest energy state contains fluctuations. Near an event horizon, these fluctuations produce a measurable outcome for distant observers' thermal radiation. The consequence was startling. Black holes have temperature. They radiate energy. Over extremely long timescales, they evaporate. And when Hawking computed the entropy associated with this radiation, it matched Bekenstein's proposal exactly. The entropy was proportional to the surface area of the event horizon measured in Planck units, not to the three-dimensional volume enclosed. This result did not rely on speculation. Every constant involved is less than #0. 5# is greater than the speed of light, the gravitational constant, Planck's constant, Boltzmann's constant, was already known from experiment. The shock lay in their combination. Physics was asserting that the maximum number of distinct internal configurations a black hole can have is counted by its surface, not its depth. Why the surface? Because for any observer outside the black hole, the event horizon is where causal influence ends. Signals crossing it never return. If information is not allowed to vanish, an assumption deeply rooted in quantum mechanics, then information must remain encoded in the only structure that still interacts with the outside universe. That structure is the boundary. This realization sharpened into a deeper problem. If Hawking radiation is purely thermal and random, then once a black hole fully evaporates, all information about what fell in appears lost, is less than #0. 5# is greater than. This contradicts a foundational principle of quantum mechanics. The evolution of physical states preserves information. This conflict became known as the black hole information paradox. The paradox is not abstract. It is a stress test for the internal consistency of modern physics. If information is truly destroyed, quantum mechanics fails at a fundamental level. If information survives, then Hawking radiation must carry subtle correlations beyond simple thermal noise. And if such correlations exist, the event horizon cannot be a featureless surface. It must possess microscopic structure capable of storing and releasing information over time. How could a surface remember? Popular explanations compare the horizon to a cosmic hard drive. The analogy helps intuition, but hides the real mechanism. What matters physically is the behavior of time and energy near the horizon. From the perspective of a distant observer, matter approaching the horizon appears to slow down its signals, stretched and redshifted. The object never quite crosses the boundary in finite external time. Its information becomes increasingly compressed into an ever thinner layer near the horizon. This is not illusion. It is a direct consequence of gravitational time dilation, predicted by general relativity and confirmed by experiments involving clocks in gravitational fields, is less than #0. 5# is greater than. The same physics applies near black holes, only far more intensely. Modern observations reinforce the reliability of this framework. X-ray observatories, operated by NASA and ESA, have measured emissions from accretion disks, heated to millions of Kelvin, orbiting just outside predicted event horizons. The timing and spectra of these emissions match models of strong gravity with remarkable precision. The Event Horizon Telescope added a crucial observational anchor. Its images of the black hole shadow in M87 and Sagittarius A star reveal the gravitational bending of light around the horizon. While these images do not show the horizon directly, their size and shape are consistent with predictions from general relativity. The objects under discussion are not theoretical abstractions. They are real astrophysical systems. The deeper implication emerges from entropy itself. In physics, entropy counts the number of microscopic configurations compatible with a macroscopic description. When entropy scales with area, it means the number of allowed microscopic states of a region scales the same way. This forces a revision of how physical degrees of freedom are distributed in space. Ordinary intuition says that larger volumes hold more detail. Black hole thermodynamics says otherwise. Information capacity is capped by boundary area, is less than #0. 5 hash is greater than. If this is true for black holes, the densest possible objects, then no ordinary system can exceed this limit. The boundary rule applies universally. Efforts to resolve the information paradox led to ideas such as black hole complementarity, which suggests that information can be both reflected at the horizon and pass through it depending on the observer without contradiction. So Yu Jinghao Lin, 5 hash is greater than. Later developments explored how subtle correlations in Hawking radiation could gradually return information without violating causality or known physics. In every approach, the horizon plays a central role as the carrier of information. Why preserve quantum mechanics at all costs? Because it works. From atomic spectra to lasers, from semiconductors to quantum interference, the predictive success of quantum theory is unmatched. Modern technology exists because quantum evolution preserves information with extraordinary precision. Abandoning that principle would unravel the foundation of experimental physics. The sequence of discoveries is therefore not optional. Bekenstein introduced entropy to protect thermodynamics. Hawking demonstrated radiation to protect quantum field theory. The information paradox exposed a deeper constraint, and the solution space consistently points toward the same conclusion. If physics is to remain coherent, information must be stored at boundaries. The event horizon is no longer a simple geometric surface. It is where gravity, quantum mechanics, thermodynamics, and information theory intersect. Its properties are dictated by constants measured in laboratories, confirmed by astronomical observations, and tested indirectly by space-based instruments operated by NASA and ESA. As these pieces come together, a clearer picture begins to form. If the interior of a black hole cannot function as an accessible store of information, and if information itself cannot be destroyed, then the full description of the system has no place to reside except on its boundary. Following that logic to its limits leads to a consequence that reaches beyond black holes alone, is less than #0. 5 hash is greater than the possibility that gravity itself may not be fundamental, but instead arise from the way information is organized on a distant surface. Par 3, could gravity be a shadow of something happening on a distant surface? Gravity looks like the most direct fact in nature, yet black holes force an uncomfortable possibility that nothing pulls at all. And what we feel as weight may be the bookkeeping of information written somewhere else. By the time Leonard Susskind began pushing the holographic principle into a full research program, gravity had already survived more than 2 centuries of hard testing, is less than #0. 5 hash is greater than Newton's law predicted planetary motion with extraordinary accuracy. Einstein's general relativity corrected Newton, where precision demanded it, explaining Mercury's extra-orbital precession and predicting the bending of light by mass later measured during eclipses and now observed routinely through gravitational lensing. Today, that same geometry is built into practical systems. Satellite navigation depends on gravitational time dilation corrections because clocks in orbit tick at a measurably different rate than clocks on Earth's surface. And when LIGO and Virgo detect gravitational waves from merging black holes, the waveforms match the relativistic predictions for compact objects with horizons. In other words, gravity is not an optional idea. It is a measured working description of nature. So when Susskind and others speak about gravity as emergent, they are not dismissing gravity. They are challenging what kind of thing gravity is at the most fundamental level. The motivation comes from a chain of constraints that began with black hole thermodynamics. In part 2, the horizon became more than a geometric boundary. It became a surface whose area sets the maximum entropy, and therefore the maximum information content for a region. That result is not a philosophical statement. It is a quantitative limit derived from combining quantum field theory, thermodynamics, and relativity. Here is the pressure that builds from that limit. In ordinary intuition, a three-dimensional volume seems to contain the fundamental details of what is inside it. But black holes indicate that at maximum density, the count of possible microscopic states is set by surface area. If nature truly enforces this as a universal bound, then any complete description of a region cannot require more independent degrees of freedom than the boundary allows. That is the first step toward emergent gravity. It turns the boundary into the place where the inventory is stored. Susskind sharpened this into a practical research stance. He argued that a gravitational system in a volume can be equivalent to a non-gravitational quantum description living on a boundary is less than #0. 5# is greater than. This is more than a metaphor. It is a claim about how many variables are needed to describe physics without contradiction. If the boundary description is complete, then the interior gravity is not added as a separate fundamental ingredient. It appears as a large-scale behavior of the boundary information. To understand why that is not mere wordplay, it helps to hold two facts side by side. First, gravity couples to energy and momentum in a universal way. Everything with energy participates, regardless of charge or composition. Second, entropy and information are also universal. They do not care whether a system is made of gas, molecules, photons, or quantum fields. Entropy counts possibilities. Information describes constraints on those possibilities. When black holes force entropy to the boundary, they are forcing the universal accounting to the boundary too. Now place this next to another experimental reality. Is less than #0. 5# is greater than. The only reason we can speak confidently about black holes at all is that strong gravity astrophysics has become observational. X-ray telescopes have measured hot, inner accretion flows near compact objects with spectra shaped by relativistic motion and gravitational redshift. Radio interferometry through the Event Horizon Telescope has imaged the shadow-like structure around supermassive black holes, consistent with light bending and photon orbits in curved spacetime. Gravitational waves have turned mergers into timed signals. These observations confirm the macroscopic behavior of horizons and spacetime curvature. They do not yet reveal microscopic information storage, but they establish that the arena where holography matters is not imaginary. It is part of the sky. Suskind's move was to treat the area law as a signpost, then ask what it implies for gravity itself is less than #0. 5# is greater than. If a gravitational region is fully describable by boundary degrees of freedom, then gravity in the interior is not fundamental in the same sense as the boundary quantum rules. It becomes comparable to thermodynamic behavior. Temperature is real, measurable, and predictive, yet it is not a fundamental variable of microscopic physics. It arises from statistics of many degrees of freedom. In this view, gravity could be like temperature. a reliable emergent description that appears when information is organized in certain ways. There is a reason this analogy has force in physics. Black holes already behave like thermodynamic systems. They have entropy proportional to area and temperature proportional to surface gravity. They obey versions of the first and second laws of thermodynamics, linking changes in mass-energy horizon area and radiation. This is not a storytelling device. It is a mathematical structure that matches every consistency check we have. Once a gravitational object behaves thermodynamically, it becomes reasonable to wonder whether gravity itself has a statistical origin. This is where the phrase spacetime emergence enters the technical conversation. It does not mean spacetime is unreal. It means spacetime geometry might be a derived description built from deeper quantum relationships, is less than #0. 5# is greater than. A key ingredient is entanglement, the quantum correlation that links measurement outcomes between separated systems in ways no classical probability can reproduce. Entanglement is not exotic in the modern lab. It is a working resource in quantum computing and quantum communication experiments. If entanglement patterns define how information is shared, and if boundary information is complete, then the geometry we call distance and curvature may reflect those patterns. This sounds abstract until it is tied back to a concrete gravitational phenomenon. In general relativity, curvature tells matter how to move, and matter energy tells curvature how to change. In an emergent picture, curvature becomes a coarse-grained summary of how information is distributed and entangled. Changes in what we call gravitational fields correspond to changes in informational structure, not to a new fundamental force carrier. That is the claim that gravity could be a shadow of something happening on a surface. The word shadow is useful because it points to a relationship between a higher detail description and a lower detail projection. A shadow is not fake. It is incomplete. It carries real information about shape and motion, while discarding other details. In the same way, emergent gravity would be the effective description we see when we ignore the microscopic boundary bookkeeping and track only macroscopic behavior inside. The gravitational field becomes a summary statistic. There is also a practical reason researchers take this seriously. Quantum gravity remains unsolved. We have no complete theory that merges quantum mechanics and general relativity at the smallest scales, is less than #0. 5# is greater than direct experiments at the Planck length are beyond any foreseeable accelerator technology. Yet black hole thermodynamics offers a rare place where both theories speak at once. If holography provides a mathematically consistent bridge, it becomes one of the few routes to testable predictions at accessible scales through indirect constraints on entropy, information flow, and consistency with observed horizons. To keep this grounded, consider what we can already measure in cosmology that depends on gravity's large-scale behavior. Gravitational lensing maps mass distributions, including dark matter, because lensing responds to total gravitational potential rather than visible light. Space telescopes have observed lensing arcs and multiple images of background galaxies behind clusters, allowing reconstruction of the mass profile. The same lensing also acts as a natural telescope, magnifying very distant galaxies and letting modern observatories study the early universe. Every lensing measurement is a test that gravity behaves as geometry on scales from galaxies to clusters. Now consider the holographic constraint again. If a region's information content is capped by area, then the gravitational degrees of freedom inside that region cannot be independent beyond that cap, is less than #0. 5# is greater than this, pushes against the naive idea that spacetime is a continuum with infinitely many independent points, each carrying its own independent data. Continuum mathematics works extremely well as an approximation, but holography suggests the fundamental count is finite per unit area in Planck units. In such a world, geometry is a derived smooth limit of discrete information. Susskind's arguments gained traction because they did not depend on sentiment or preference. They were forced by avoiding contradictions. If black hole evaporation preserves quantum information, then the horizon must encode it. If the horizon encodes it, then the count of internal states is set by area. If the count of internal states is set by area, then a boundary description has the right size to be complete. If a boundary description can be complete, then interior gravity may be emergent. Each step is a response to a constraint, not a decorative idea. Even so, the emergent gravity picture remains incomplete. It must match every precision test of general relativity. It must reproduce gravitational wave propagation, lensing orbital dynamics, and time dilation. It must also respect the local behavior we see in laboratories where physics appears local and causal at accessible scales. Any successful framework has to show how locality emerges from boundary information without breaking what experiments already confirm. This is where the work becomes technical and where many proposals fail. The value is that the constraints are sharp. Nature will not accept vague stories here. There is a short sentence from John Archibald Wheeler that fits this point in the cleanest possible way. It from bit. Wheeler was not offering comfort. He was pointing to a hard direction in theoretical physics, the possibility that physical reality, including geometry, is built from information. In the context of holography, that phrase becomes a specific research target rather than a slogan. If bits on a boundary can generate the "it" of interior gravity, then gravity is not fundamental. It is the macroscopic outcome of information constraints. One more observational anchor matters here, because it keeps the discussion tied to the sky is less than #0. 5# is greater than. When astronomers observe black holes feeding, they see energy extracted from gravitational potential and converted into radiation and jets. The efficiency of that conversion depends on the spacetime geometry close to the horizon, including the black hole's spin. X-ray timing and spectroscopy constrain those parameters. Gravitational waves constrain mass and spin during mergers. These are not small details. They are measurements of geometry as a physical actor. Any emergent picture must reproduce them as accurately as general relativity already does. The focus here is not that gravity is optional or that space is an illusion. It is that gravity may be an effective description of deeper rules that track information on boundaries. From that perspective, the interior world is not discarded. It is reconstructed. That reconstruction is constrained by entropy limits, quantum correlations, and by the requirement that information not be destroyed. This is why the idea remains under active consideration. It is anchored to the most restrictive accounting rules nature has revealed so far. Following this line of reasoning leads directly to a setting where the idea can be tested with precision, a mathematical framework in which a universe with gravity is shown to be fully equivalent, detail by detail, to a quantum description, without gravity living on its boundary. Bart Katz. Did string theory accidentally reveal that our universe has fewer dimensions than we think? The moment the equations were checked line by line, it became clear that a universe filled with gravity could be fully described by a world without. Gravity living on its boundary, and that realization unsettled nearly every assumption physicists held about dimensions. The story of this part does not begin with cosmology, nor even with black holes, but with an internal struggle inside theoretical physics during the late 1990s. String theory had grown into a vast mathematical framework capable of unifying gravity with quantum mechanics, but it carried a heavy cost. It demanded extra dimensions of space, more than the three we observed directly. These dimensions were assumed to be compact, curled up at scales far smaller than any experiment could probe. For many years, this feature was treated as a technical necessity rather than a physical statement about the universe. Then, in 1997, Juan Maldacena published a paper that quietly reorganized the field. He did not claim to describe our universe. He studied a mathematically well-defined spacetime known as anti-de Sitter space, a universe with constant negative curvature, unlike the expanding cosmos we inhabit. But what he discovered, inside this idealized setting, was precise, testable, and deeply unsettling. Maldacena showed that a theory with gravity in a higher dimensional anti-de Sitter space is mathematically equivalent to a quantum field theory, with no gravity living on its lower dimensional boundary, is less than #0. 5# is greater than every physical quantity on one side had a direct counterpart on the other. Energies, correlations, symmetries, and dynamics matched exactly. This was not analogy or metaphor, it was equivalence. Two radically different descriptions, one involving curved spacetime and gravity, the other involving quantum fields on a flat boundary, produced the same physics. This result became known as the ADS-CFT correspondence. Its power lies not in its name but in what it enforces. If the correspondence is correct, then gravity inside the bulk spacetime is not an independent ingredient. It is fully encoded by a theory that has no gravity at all. In this setting, the higher dimensional universe does not contain more information than its lower dimensional boundary. The boundary description is complete. At first, many physicists assumed this was a special coincidence. Anti-de Sitter space is highly symmetric. Conformal field theories possess mathematical properties that make calculations tractable. Perhaps the correspondence worked only in this artificial environment. But as years passed, the evidence accumulated that this was not a curiosity, but a structural insight. The correspondence passed every internal consistency check. Calculations performed on one side reproduced results on the other, even in regimes where traditional methods failed. What makes this relevant to our discussion is not whether our universe is exactly anti-de Sitter. It is what the correspondence implies about dimensions themselves. In ADS-CFT, the number of dimensions in which gravity operates is larger than the number of dimensions needed to describe the physics completely. The extra dimension behaves like a bookkeeping direction. It tracks how quantum information is organized, not an independent spatial arena filled with new degrees of freedom. This changes how dimensions are interpreted. In classical physics, adding a dimension adds new places where things can happen. In holographic physics, adding a dimension may simply reorganize existing information. The bulk dimension emerges from the boundary description as a way to encode scale and correlation. Deeper regions of the bulk correspond to different energy scales in the boundary theory. Distance in the gravitational direction translates into how information is coarse-grained. This mapping is not poetic, it is operational. When physicists compute correlation functions on the boundary, they can interpret those results as particle interactions and fields propagating through a curved higher dimensional spacetime. The bulk geometry is reconstructed from boundary data that is less than #0. 5# is greater than. In this sense, spacetime itself becomes a derived object, assembled from quantum information rather than assumed at the start. It is important to pause here and remain precise. The correspondence does not say that space is fake or that dimensions vanish. It says something subtler and far more restrictive. It says that the minimal description of physical reality may require fewer dimensions than the effective description we use to organize phenomena. The extra dimension is useful, predictive, and real in practice, but not fundamental in the accounting of information. This idea resonates strongly with the entropy bounds encountered earlier. If a region's maximum information content is controlled by its boundary area, then describing physics using a bulk volume risks overcounting degrees of freedom. AdS-CFT avoids this problem by construction. Soujingholing 5 hash is greater than. The boundary theory contains exactly the right number of variables to saturate the entropy bound. Gravity appears in the bulk only as a way of efficiently organizing those variables. Although the correspondence lives in theoretical physics, it has influenced how researchers interpret real astronomical data is less than #0. 5 hash is greater than. For example, black hole thermodynamics, studied through holography, has sharpened predictions about how information must flow during black hole evaporation, even if those details are not directly observable yet. These predictions must remain compatible with the macroscopic behavior measured by observatories operated by NASA and ESA, which track accretion disks, relativistic jets, and gravitational lensing near compact objects. The relevance of AdS-CFT is also practical inside physics itself. It has been used to study strongly interacting quantum systems that cannot be solved by standard methods. Problems in nuclear physics, condensed matter systems, and quark-gluon plasmas have been explored using gravitational duals. In these cases, gravity is not the target of study. It is a computational tool standing in for a difficult quantum calculation. That such a translation works at all reinforces the idea that gravity may be an emergent language rather than a primitive one. The historical context matters. String theory did not set out to reduce dimensions. It attempted to quantize gravity consistently. The holographic insight emerged as a byproduct of demanding mathematical consistency and unitarity. The theory resisted contradictions, and in doing so, it revealed that fewer dimensions were needed to encode the same physics. This was not design. It was constraint-driven discovery. One reason the correspondence has endured is that it is unforgiving. If a proposed gravitational theory in the bulk violates basic principles such as causality or energy conservation, the boundary theory reflects the inconsistency immediately. The two descriptions stand or fall together. This mutual enforcement is rare in theoretical physics and gives researchers confidence that they are not dealing with an interpretive artifact. The deeper implication is uncomfortable but precise. If gravity and spacetime geometry can be translated into quantum information living on a boundary, then spacetime is not the stage on which physics happens. It is part of the script. Is less than #0. 5 hash is greater than. The stage directions are written in information and geometry is how those directions are read at large scales. It is also crucial to note what AdS-CFT does not yet do. It does not describe our accelerating universe directly. Our cosmos appears closer to de Sitter space, with positive curvature driven by dark energy. Extending holography to that setting remains an open challenge. Observations from cosmic microwave background measurements and large-scale structure surveys have not revealed a natural anti-de Sitter geometry. The mismatch is real and acknowledged. Yet the correspondence still matters because it establishes that holography is not a vague idea. It can be exact. It can be calculational. It can replace one physical description with another without loss of predictive power. Is less than #0. 5 hash is greater than. Any future holographic description of our universe must meet this standard. It must reproduce cosmological observations with the same fidelity that AdS-CFT reproduces quantum field dynamics. The universe does not owe us simplicity, but it does obey consistency. ADS-CFT exists because consistency demanded it. Once gravity, quantum mechanics, and information were forced to agree, a lower dimensional description became unavoidable in that setting. Here, one constraint still refuses to settle. In certain geometries, a universe with gravity can be fully described by a lower dimensional theory living on its boundary. But our universe does not appear negatively curved. It appears to be expanding, with no obvious edge in sight. The problem no longer lies in whether holography can work in principle, but in identifying what could possibly play the role of a boundary in a universe that seems to have none at all. Part 5. If our universe is expanding, where is its edge supposed to be? If the holographic principle is truly fundamental, then a deeply unsettling tension appears at the heart of modern cosmology. Our universe is expanding, and that expansion is accelerating. So where could a boundary possibly exist that is strict enough to store the information of spacetime itself? In the earlier parts of this series, holography emerged from hard limits, not from preference, is less than #0. 5# is greater than black holes, forced entropy to scale with the area of their horizons, a result that followed inevitably once thermodynamics, quantum mechanics, and gravity were required to agree. From that point on, the idea that the interior of a region might require fewer fundamental degrees of freedom than its volume suggests became difficult to ignore. In ADS-CFT, this idea reached its most precise expression, where a gravitational universe could be fully equivalent to a lower dimensional quantum theory living on a boundary. But the universe we observe is not anti-de Sitter. Astronomical data tell a different story. Observations of type Ia supernovae in the late 1990s revealed that cosmic expansion is accelerating. This result, later confirmed by measurements of the cosmic microwave background and large-scale structure, led to the 2011 Nobel Prize in Physics. A simple and remarkably successful description introduces a background energy component, now called dark energy, which today accounts for roughly 70% of the total energy density of the universe. Data analyzed by missions operated by NASA and ESA consistently support this picture. When dark energy dominates, the large-scale geometry of spacetime approaches what physicists call de Sitter space, a spacetime with accelerating expansion. This is where the holographic story becomes sharply more difficult. In anti-de Sitter space, the boundary is geometrically well-defined and static. In de Sitter space, there is no spatial boundary at infinity where information can be cleanly placed. Instead, the universe contains horizons that arise from causal structure rather than geometry alone. These horizons are not material walls. They emerge because the speed of light is finite, and because space itself expands. There are regions of the universe whose light has not yet reached us, and regions whose light never will if acceleration persists indefinitely. The observable universe is therefore finite, not because space ends, but because information access is limited. The present radius of the observable universe is about 46.5 billion light-years, or roughly 14.3 gigaparsecs, even though the universe itself is only about 13.8 billion years old. This apparent mismatch is a direct consequence of expansion occurring while light travels. Here, holography encounters its central cosmological challenge. If the boundary is merely an observer-dependent horizon, then where is the global repository of information? If every observer has a different horizon, how can a single, consistent quantum description exist? These are not philosophical puzzles. They are technical constraints on any attempt to build a quantum theory of gravity that applies to an accelerating universe. One reason physicists continue to take this challenge seriously is the thermodynamics of de Sitter horizons is less than #0. 5# is greater than In a universe with accelerating expansion, the cosmological horizon behaves in strikingly similar ways to a black hole horizon. It can be assigned a temperature and an entropy proportional to its area, a result first derived by Gibbons and Hawking. This entropy-area relationship suggests that even without a spatial boundary at infinity, nature still associates a finite information capacity with causal horizons. This leads to a compelling but unresolved line of reasoning. Is less than #0. 5# is greater than. If every causal patch in a de Sitter-like universe carries a finite entropy, then each patch corresponds to a finite number of quantum states. A complete quantum description of cosmology may therefore need to be built from these causal patches, rather than from a single global state defined over all of space. Several approaches in holographic cosmology explore this direction, but none yet achieve the mathematical clarity of AD-CFT. Dark energy makes this problem sharper rather than softer. Measurements of the cosmic microwave background by the Planck satellite show that a nearly flat universe, with dark energy accounting for about 0.68 of the total energy density, fits the data extremely well. At the same time, local measurements of the Hubble expansion rate using Cepheid variables and supernovae yield a higher value than that inferred from early universe data. Observations from the James Webb Space Telescope have reinforced that this discrepancy, known as the Hubble tension, cannot be easily dismissed as a measurement error. Why does this matter for holography? Because the detailed history of cosmic expansion determines the structure and evolution of cosmological horizons. If the expansion history is not fully settled, then the nature of the effective boundary that limits information is also unsettled. In AD-CFT, the boundary is fixed by geometry. In an accelerating universe, any candidate boundary is dynamic and model-dependent. This forces holographic cosmology to remain tightly anchored to observational data rather than abstract symmetry alone. A careful approach begins with boundaries that astronomy already demands we acknowledge. The particle horizon defines how far light has traveled since the beginning of cosmic expansion. The event horizon defines which regions can ever influence us in the future. The Hubble radius marks where recession speed, due to expansion, reaches the speed of light. In a universe dominated by dark energy, these horizons do not coincide. Their separation is not a technical nuisance. It is the structure that any holographic description must respect. Another subtle point is often overlooked in simplified explanations. A boundary in cosmology is not defined only by distance. It is defined by causal accessibility over time. Two regions may be far apart, yet still exchange information in the future if expansion slows. In an accelerating universe, that exchange can be permanently cut off. Dark energy therefore reshapes causal structure itself. This is why it plays such a central role in discussions of holographic limits. Seen this way, the holographic principle acquires a more disciplined form. Is less than #0. 5# is greater than in black holes. The horizon is a one-way causal surface, and the area law appears as an absolute limit. In an accelerating universe, the cosmological horizon is also a causal boundary, but one whose properties depend on the expansion history. If entropy is associated with this horizon in the same way, then the information content of the observable universe is finite and evolves with cosmic time. This has led researchers down multiple paths. Is less than #0, 5# is greater. Some attempt to construct a de Sitter version of holography, often referred to as DS, CFT, though defining a consistent boundary theory in this setting remains difficult because time behaves differently than in anti-DA. Sitter space. Others focus on local causal patches, treating each horizon as a fundamental unit and exploring how quantum descriptions might be stitched together consistently. Both approaches are constrained by cosmological observations, because de Sitter space is only an approximation to the real universe, which also contains matter, radiation, and structure formation. The role of JWST in this discussion is indirect but important. By pushing distance measurements and early galaxy observations to higher precision, it tests the assumptions built into the expansion history. If that history requires revision, then the evolution of horizons and associated entropy bounds must be revisited as well. Holographic cosmology cannot proceed independently of these results. It must remain compatible with what the sky reveals. One argument that continues to persuade researchers is methodological restraint. Dark energy is required by observation. Accelerated expansion is measured. Cosmological horizons exist as a consequence. These are facts. What is not yet required is a global boundary identical to that of ADS. A cautious holographic approach therefore begins with the cosmological horizon itself as a candidate information boundary and asks whether area-based entropy, effective temperature, and information limits lead to testable consequences that agree with observation. There is an uncomfortable convergence here, is less than #0. 5# is greater than, on one hand, standard cosmology describes the cosmic microwave background and large-scale structure with remarkable success. On the other, that same framework implies a horizon with finite entropy, suggesting that the observable universe has a finite number of quantum states. If that is true, then treating spacetime as a continuum with infinitely many independent degrees of freedom is an approximation, albeit an extraordinarily accurate one at accessible scales. No final conclusion is required to see where the pressure is building. If holography holds for black holes, and if cosmological horizons share the same entropy area structure, then a holographic formulation of cosmology must explain why we observe a nearly flat universe with dark energy around 70%, and why horizon scales align with the measured expansion history. Models that cannot meet these constraints will not survive contact with data. As these constraints tighten, the cosmic microwave background becomes impossible to ignore. If the universe's information content is limited by horizon area, then the primordial fluctuations that later grew into galaxies may still carry faint traces of that limit. Those traces would not take the form of symbols or slogans, but of precise constraints on correlations, on angular power spectra, and on how finely spacetime itself could be resolved in the early universe. Within those faint patterns preserved in the oldest light, we can observe the problem of identifying a holographic boundary in an expanding universe begins to tighten around a smaller set of possibilities. Part 6. Could tiny fluctuations in the cosmic microwave background be pixelation of reality? If the oldest light in the universe is already telling us that spacetime has a finite information capacity, then the cosmic microwave background may be less like a smooth backdrop and more like a test pattern that exposes the resolution limit of reality. The cosmic microwave background, often shortened to CMB, is not a decorative feature of cosmology. It is measured radiation filling the sky with a temperature close to 2.725 Kelvin, arriving from every direction with almost the same intensity. This light was released when the universe cooled enough for electrons and protons to combine into neutral hydrogen, allowing photons to travel freely, instead of being scattered constantly by charged particles. In practical terms, the CMB is a snapshot of the universe when it was about 380,000 years old. long before any star or galaxy existed. The reason this part matters for holography is simple and strict. If the universe has a fundamental limit on information per horizon area, then early universe fluctuations cannot encode unlimited detail. The CMB is the cleanest screen we have for that era, because it comes from a time when matter was still close to uniform, and the dominant signals were small variations in density and temperature. Those variations are tiny, about 1 part in 100,000, yet they seeded everything we see today, from galaxies to clusters. The CMB is therefore both precise and unforgiving. If a fundamental resolution limit exists, it has very few places to hide. The modern era of this story begins with an instrument that changed cosmology by making the CMB visible as a measurable pattern rather than a theoretical prediction. NASA's COBE satellite, launched in the late 1980s, confirmed the spectrum of the CMB to be extremely close to a perfect blackbody, and then detected the first anisotropies, the tiny temperature variations across the sky. That detection was not a small technical milestone. It established that the early universe had structure at the level needed to form galaxies, and that the pattern could be measured and compared to physical models. COBE did not have the angular resolution to see the fine detail. That came next. NASA's WMAP mission, launched in the early 2000s, mapped the anisotropies with much higher precision and produced a power spectrum that matched a universe dominated by cold dark matter and dark energy with a nearly flat geometry. Then, ESA's Planck mission, launched in the late 2000s, improved the measurement again, tightening uncertainties and extending the map to smaller angular scales. Planck's maps are not just prettier, they reduce ambiguity. They squeeze the range of allowed models by making more of the sky's statistical structure visible. Those measurements already imply something important about resolution, even before any speculative ideas are introduced. The CMB anisotropies are not arbitrary. Their pattern shows acoustic peaks, the imprint of sound waves in the hot plasma of the early universe. The positions and heights of those peaks tell us about the composition of the universe, the amount of ordinary matter, dark matter, and the way light and matter coupled before recombination. This is physics, performed at cosmological scale, but it is physics with the same discipline as a laboratory spectrum. The remarkable fit of the standard model of cosmology to these data means that any new effect, including a hypothetical pixelation of spacetime, has very little room to modify the pattern without being noticed. So what do researchers actually mean when they talk about pixelation or spacetime quantization in this context? They do not mean that the sky is made of squares. They mean something more constrained. If space-time is ultimately described by a finite number of degrees of freedom per unit area, then there may be a smallest meaningful increment of information. In a holographic picture, that increment is often discussed in relation to Planck scale units, but the important point is not the number itself. The important point is that there is a maximum information density, and that maximum could in principle influence correlations in the early universe fluctuations. The standard cosmological model treats the primordial fluctuations as a nearly Gaussian random field with a specific spectrum shaped by inflationary physics or by whatever mechanism generated the initial perturbations. Planck tested that Gaussianity to high precision. It also tested statistical isotropy, the expectation that the statistical properties are the same in every direction. Most features match the simplest expectations well. Yet a handful of features have remained discussed for years because they sit near the edge of statistical significance, not strong enough to declare a discovery, but persistent enough to keep attention. Examples include the low quadrupole amplitude compared to the simplest predictions, hemispherical power asymmetry, and the well-known cold spot. Each of these can be produced by chance in a Gaussian field, and the look elsewhere effect makes it easy to exaggerate their meaning if one is not careful. Still, these features are valuable because they teach researchers how to search for non-standard correlations. If spacetime had a resolution limit that introduces a particular kind of noise or a particular cutoff in correlations, it might show up in anomalies of this kind. The discipline is that the pattern must be predicted quantitatively and then compared to the sky not chosen after the fact. The holographic angle enters when the focus shifts from individual anomalies to global limits on information. If the degrees of freedom of a causal patch are finite, then correlations across the sky might be bounded in a way that looks like an upper limit on independent modes. In plain terms, there may be fewer independent patterns available than a naive continuum model would allow. That would not necessarily produce a dramatic signature. It might produce subtle departures from the expected distribution of correlations at the largest angular scales, or an effective noise floor that does not integrate away with more observing time. This is where the phrase holographic noise appears in some literature. The idea is that if position and geometry are derived from underlying information, then there may be an irreducible uncertainty in transverse distances linked to the finite information content on a boundary. Researchers have proposed that such uncertainty could be detectable using interferometers instruments that measure relative lengths by tracking how light waves interfere. The most prominent experimental effort in this direction was the holometer at Fermilab, designed to search for correlated noise that could reflect a fundamental space-time jitter at extremely small scales. The key point for viewers is the scientific posture. These proposals did not remain on paper. They were turned into hardware designed to fail loudly if the idea was wrong. The outcome matters. The holometer did not find the specific type of holographic noise it was designed to detect, placing strong constraints on certain models. That does not kill holography as a broad principle, because holography in ADS, CFT, and black hole thermodynamics is not the same thing as any particular noise model in an interferometer. But it does show that nature does not permit every imaginative version of pixelated spacetime. Experimental constraints already remove large regions of possibility space. Gravitational wave detectors, such as LIGO, measure tiny changes in arm lengths on the order of a fraction of a proton's diameter over kilometers of baseline. Their noise budgets are understood in detail from thermal motion to quantum shot noise. If spacetime itself contributed an additional correlated noise floor of a certain kind, it could, in principle, become visible in these instruments or in future detectors. The fact that we can account for the observed noise with known physics is itself a constraint on exotic proposals. Now return to the CMB with that mindset. The CMB is not measured by one instrument once. It is cross-checked. Different detectors, different scanning strategies, different foreground subtraction methods, and independent analyses have been used across decades. The measured angular power spectrum is therefore not a fragile artifact. It is one of the most robust datasets in the whole of astrophysics. If a pixelation signature exists, it has to survive this gauntlet. It must predict a pattern that remains after foregrounds are removed and after systematic errors are accounted for. What kinds of signatures are even plausible without contradicting what Planck already confirmed? One possibility is a cutoff in correlations at the largest scales linked to a finite information budget per horizon. Another is a specific form of non-Gaussianity, not arbitrary but with a shape tied to boundary encoding constraints. Another is a departure from perfect statistical isotropy that follows a consistent rule rather than appearing as a collection of unrelated oddities. Each of these is difficult because Planck placed strong bounds on non-Gaussianity and because the standard model already fits the main features extremely well. The challenge is therefore not to produce a new effect. The challenge is to produce a new effect that is both small enough to evade existing constraints and structured enough to be distinguishable from chance. There is also an important scaling issue that often gets overlooked in casual discussions of smallest units. The Planck scale is unimaginably small, while the CMB pattern spans the entire sky. To connect the two, a model must explain how microscopic discreteness propagates into macroscopic correlations without being washed out by cosmic expansion and by the physics of the plasma. This is where many proposals fail, not because the ideas are weak in spirit, but because the chain of causation is hard to make quantitative. A credible proposal must track how initial conditions at extreme energies translate into the statistics of temperature anisotropies measured today. The reason researchers still pursue this is that the reward would be unusually clean. A confirmed fundamental information limit imprinted in the CMB would not be an incremental parameter tweak. It would be a clue about quantum gravity, a domain where direct experiments are nearly impossible. It would connect horizon, entropy, holography, and cosmological observation in one measurable thread. That is why the search continues, even under tight constraints. JWST enters this part indirectly, but it still matters for the logic of the program. JWST does not measure the CMB. It measures early galaxies and star formation at high redshift, and it helps constrain how structure grew from the primordial seeds that the CMB reveals. If a proposed pixelation model modifies the primordial fluctuation spectrum, it will affect not only the CMB, but also the timing and abundance of early structures. The consistency between CMB-derived initial conditions and the observed growth of structure is another constraint. A model that fits one but breaks the other will not survive. There is a disciplined way to hold all of this together without forcing conclusions. The CMB provides a high-precision map of primordial statistics. Large-scale structure surveys and lensing map how those statistics evolved. Early galaxy observations test the timeline. Any claim of space-time quantization that matters macroscopically must thread through all of these datasets simultaneously. That requirement is severe, and that severity is what makes the search meaningful rather than speculative. Here the argument stands on its narrowest footing yet. If limits on information are real, then the cosmic microwave background is not simply a relic of the early universe. It becomes a quantitative constraint, one that takes broad ideas and turns them into numbers that can be tested, accepted, or ruled out. What remains is not certainty, but pressure, not slogans, but measurements. When those constraints are applied to the CMB, a deeper consequence comes into view. If space-time geometry can be reconstructed from information limits and correlations, then temperature maps alone are no longer enough. The problem reaches inward toward the mechanism that generates correlations themselves. Quantum entanglement, and the possibility that space-time is assembled from it rather than built from matter. Byproduct. Is space-time itself made of quantum information rather than matter? If gravity can emerge from boundaries and cosmology can be constrained by information limits, then the next pressure point is unavoidable. Space-time itself may not be the container of physics, but a product of how quantum information is arranged. For most of the history of physics, space and time were treated as the fixed background in which events occur is less than #0. 5# is greater than even Einstein's general relativity. Radical, as it was still assumed, space-time as the primary object, now flexible and responsive to energy and momentum, but still fundamental. Quantum theory, by contrast, never required space to be fundamental in the same way. It required states, probabilities, and correlations. The tension between these viewpoints has driven a century of work, and over the last few decades, a new pattern has emerged from that tension. The pattern suggests that space-time geometry may be reconstructed from quantum information rather than assumed from the start. The seed of this idea is often associated with a short phrase from John Archibald Wheeler, "it from bit." Wheeler did not propose a finished theory. He proposed a direction. The phrase captured the possibility that physical reality, including geometry, might arise from binary distinctions, from yes-no questions encoded in quantum systems. At the time, this sounded speculative. Today, it has become a concrete research program driven not by taste, but by constraints imposed by black holes, holography, and quantum mechanics. To see why this idea gained traction, it helps to step back to what quantum information actually means in physics. Quantum information is not about computers in a conventional sense. It is about how quantum states are correlated, how much can be known about one system by measuring another, and how those correlations evolve. Entanglement is the central feature. Two systems can be prepared in a joint state, where neither has a definite description on its own, yet the pair has well-defined properties together. This is not interpretation. It is measured routinely in laboratories through Bell tests and quantum communication experiments. What changed the conversation is the realization that entanglement is not just a detail of quantum mechanics. It appears to be structural. In holographic settings, particularly those inspired by ads, CFT researchers discovered that the geometry of spacetime can be reconstructed from patterns of entanglement in the boundary theory. Regions that are strongly entangled correspond to nearby regions in the bulk geometry. Regions with weak entanglement correspond to larger separations. Distance in this view becomes a measure of correlation structure rather than a primitive input. There are explicit calculations showing that if entanglement between parts of a quantum system is reduced, the corresponding bulk geometry becomes disconnected. Conversely, increasing entanglement can stitch spacetime together. The geometry responds to information structure in a way that mirrors how general relativity responds to energy and momentum. The equations look different, but the logic aligns. Geometry encodes relationships. One of the most influential technical insights supporting this picture comes from studies of entropy in gravitational systems. The entropy associated with a region of space-time, particularly when horizons are involved, behaves like entanglement entropy. It counts correlations between degrees of freedom inside and outside a boundary. This link was not assumed. It emerged from calculations that matched gravitational entropy formulas with entanglement measures in quantum field theories. The agreement was too precise to ignore. At this point, the phrase "spacetime from entanglement" stopped being a slogan and became a working hypothesis. Is less than #0. 5# is greater than. If spacetime geometry reflects how quantum information is distributed, then curvature corresponds to changes in entanglement structure. Flat space represents a particular uniform pattern. Curved space represents a deformation of that pattern. Gravity in this framework is no longer a force in the traditional sense. It is the macroscopic behavior of information responding to constraints. Why does this matter for actual observations? Is less than #0. 5# is greater than because any claim about the nature of spacetime must be compatible with the extraordinary precision of modern measurements. General relativity has been tested in the solar system in binary pulsars and through gravitational waves. Quantum mechanics has been tested in atomic clocks, interferometers, and particle physics. A framework where spacetime emerges from information must reproduce all of these successes. It cannot replace them. It must explain why they work so well. This requirement is what gives the information-based approach its discipline. It cannot discard locality lightly. Local physics works extremely well at accessible scales. Instead, locality must itself be emergent, arising when entanglement is arranged in a particular way. In regions where correlations are dense and regular physics appears local. In extreme situations, such as near horizons or at Planck scale densities, that appearance may break down. The theory must explain both regimes without contradiction. There is a historical parallel that helps make this less abstract. Temperature was once treated as a fundamental property of matter. With the development of statistical mechanics, temperature was reinterpreted as a collective measure of microscopic motion. The laws of thermodynamics did not disappear. They became emergent descriptions with precise domains of validity. In the same way, spacetime geometry may be an emergent description of underlying quantum information, valid and predictive at large scales, but not fundamental in the microscopic accounting. The difference is that we cannot yet look directly at the microscopic degrees of freedom underlying spacetime. We infer their existence from limits. Black hole entropy limits information density. Holography limits degrees of freedom per area. Cosmological horizons limit accessible information. Each limit points to the same conclusion, that spacetime cannot support unlimited independent data. Something more economical must be at work. Quantum information provides that economy. Information is counted in discrete units. Entanglement constrains how those units can be arranged. Geometry emerges as a bookkeeping device that summarizes those constraints at large scales. This view does not deny matter. Matter becomes one pattern of excitation within the information network. Fields become collective variables. Geometry becomes relational. This approach also sheds light on why spacetime behaves smoothly, even if its underlying description is discrete. In many-body quantum systems, smooth collective behavior emerges from discrete components. Sound waves propagate through a crystal, even though the crystal is made of atoms. The wave description is not wrong. It is effective. In the same way, smooth spacetime may emerge from discrete informational building blocks when viewed at scales much larger than the fundamental units. The role of experiments remains central. Quantum information theory is not a purely abstract discipline. Entanglement is measured, manipulated, and used in real devices. Precision measurements of spacetime, such as those performed by atomic clocks and gravitational wave detectors, test how geometry behaves under extreme conditions. Any proposal about emergent spacetime must respect these results. The success of general relativity and quantum mechanics sets a high bar. Astrophysical observations provide additional anchors. Black holes observed through accretion disks, relativistic jets, and gravitational waves behave exactly as predicted by spacetime geometry. Cosmological observations show a universe whose large-scale structure evolved from small fluctuations in a way consistent with gravitational instability. These facts do not disappear if spacetime is emergent. They must be explained by it. The strength of the information-based view is that it does not try to replace these observations with something new. It tries to explain why they are inevitable outcomes of deeper constraints is less than #0. 5# is greater than. If entanglement patterns determine geometry, then the stability of spacetime, the universality of gravity, and the existence of horizons follow from information theory rather than being separate postulates. This unification is not aesthetic, it is economical. There are still open problems. Extending these ideas beyond idealized holographic models to realistic cosmology remains difficult. Understanding how time itself emerges from information is an active area of research. Connecting entanglement-based geometry to laboratory-scale experiments remains challenging. None of these difficulties are hidden. They are the focus of current work. Here, what matters is the direction set by constraints. Black holes forced information onto surfaces. Holography showed that gravity itself can be encoded on boundaries. Cosmology revealed horizons with finite entropy. Taken together, these results point toward a possibility in which spacetime is not fundamental, but a large-scale expression of underlying quantum information structure. Nothing in this picture is asserted by authority. It follows from constraints that leave little room to maneuver. Once spacetime is treated as an emergent object, built from information, the problem sharpens rather than dissolves. If reality is assembled from information, then the deepest limits we can probe are no longer set by matter or energy alone, but by how information itself can be stored, processed, and preserved at the most fundamental level. Part Wit. Why does every attempt to probe reality's smallest scale lead back to information? Every time physics tries to push past matter and energy toward the smallest possible scale, it encounters the same boundary again and again. Not a particle, not a force, but a limit on information itself. This pattern did not appear suddenly, and it did not come from a single field, is less than #0. 5# is greater than. It emerged independently in black hole physics, in quantum theory, in thermodynamics, and later in the practical mathematics of computation. Each time, researchers followed a different path, yet arrived at the same constraint. There is a maximum amount of information that can be stored, transmitted, or resolved within a given physical system. When that limit is reached, the usual descriptions in terms of space, time, and matter begin to lose their meaning. The most dramatic early signal came from black holes. When physicists asked how much entropy could be packed into a region of space, black holes provided a precise answer. The entropy did not scale with volume, as intuition suggested, but with surface area. This result was not a guess. It followed from combining quantum field theory with general relativity and thermodynamics. Once accepted, it placed an absolute upper bound on information density. Any attempt to exceed it triggers gravitational collapse. That single result forced a reframing. If information content is capped by area, then information is not a secondary bookkeeping tool. It is a physical quantity with limits enforced by the laws of nature. Energy can be added, particles can be compressed, but information cannot grow without bound. The universe appears to police its own accounting. A similar lesson appeared in quantum mechanics long before black holes entered the discussion. Quantum states are not described by definite values of position and momentum simultaneously. They are described by probabilities and correlations. Measurement does not reveal a pre-existing value. It extracts information subject to fundamental constraints. These constraints are not technical shortcomings. They are built into the structure of the theory. The uncertainty principle is not about disturbance. It is about the limits of information that can be jointly specified. As experimental techniques improved, this informational character became more explicit. Quantum systems could be prepared, manipulated, and measured in ways that made entanglement a measurable resource. Entanglement is not energy. It is not matter. It is a pattern of shared information between systems. Two particles, separated by large distances, can exhibit correlations that cannot be explained by any local classical description. These correlations have been verified in countless experiments, closing loopholes and confirming that information structure is a physical feature of the world. The connection deepened when researchers began to ask how much information a physical system could process is less than #0. 5# is greater than. In the late 20th century, work by Rolf Landauer and others established that information processing has thermodynamic costs. Erasing a bit of information requires a minimum amount of energy dissipation. This was not philosophy. It was measured. Information could not be separated from physics. It obeyed physical laws and exact bounds. At this point, the thread running through different disciplines became hard to ignore. Black holes set limits on information storage. Quantum mechanics sets limits on information extraction. Thermodynamics sets limits on information processing. Computation theory sets limits on how information can be transformed in time. Each limit uses different language, but they converge on the same conclusion. Information behaves like a conserved and constrained quantity, as real as energy or momentum. The Planck scale often appears in these discussions, but it is important to be precise about what it represents. Is less than #0. 5# is greater than the Planck length. Is not a statement that spacetime is made of tiny blocks like bricks. It is a scale derived from fundamental constants, where quantum effects of gravity can no longer be ignored. At that scale, any attempt to localize information more precisely requires so much energy that spacetime itself responds gravitationally. The attempt to probe finer detail changes the system being probed. This is why every proposal to access smaller scales circles back to information is less than #0. 5# is greater than. You cannot ask where something is without encoding that answer in information. You cannot define a region of space without specifying boundaries that carry information. When gravity is weak, these requirements are invisible. When gravity becomes strong, they dominate. The smallest scale is not defined by matter. It is defined by how much information can be meaningfully specified before spacetime reacts. The rise of quantum computing sharpened this perspective further. Is less than #0. 5# is greater than. Quantum computers do not rely on new forms of energy. They rely on exploiting quantum information, superposition, and entanglement. The theoretical limits on quantum computation are not arbitrary. They are constrained by decoherence, error correction thresholds, and fundamental noise. Once again, information is not free. It is costly to protect, costly to move, and costly to preserve. What makes this relevant to cosmology and fundamental physics is that the same language appears at vastly different scales. In a laboratory, a quantum bit must be isolated from its environment to preserve coherence. In the universe, a region of spacetime must be isolated by a horizon to define a finite information content. In both cases, boundaries matter. Without boundaries, information cannot be meaningfully counted. This boundary-centered view explains why horizons play such a central role across modern physics. Event horizons of black holes, cosmological horizons, in an accelerating universe, and even effective horizons in quantum field theory, all mark limits on information flow. They are not just geometric features. They are informational bottlenecks. Once crossed, information is no longer accessible to certain observers. Observational astronomy reinforces this perspective by repeatedly confronting us with limits rather than infinities. Telescopes operated by NASA and ESA do not reveal endless detail as resolution improves. They reveal regimes where new physical processes intervene. At high energies, particle production changes the signal. Near compact objects, gravitational redshift limits what can escape. In cosmology, horizons cap what can ever be observed. The universe consistently replaces naive extrapolation with constraint. The James Webb Space Telescope adds weight to this picture not by probing the smallest scales directly, but by testing the consistency of cosmic history. JWST observations of early galaxies constrain how initial information in primordial fluctuations was amplified into structure. Any proposal that modifies the information content of the early universe must still reproduce the observed timeline of galaxy formation. Information limits are not abstract. They leave fingerprints across cosmic evolution. It is tempting to frame this convergence as a philosophical revelation, but the strength of the argument lies elsewhere. Information keeps reappearing because it is the quantity that remains well-defined when other concepts break down. At extreme densities, particles lose individuality. At extreme energies, fields fluctuate violently. At extreme curvature, spacetime geometry becomes unstable. Information, however, remains countable. It provides a language that survives where others fail. This does not mean that matter and energy are secondary or illusory. It means that at the deepest level, we can currently probe their manifestations of information arrangements rather than the primitives themselves. Matter carries information. Fields transmit information. Geometry constrains information. When pushed to their limits, all descriptions reduce to statements about what can be distinguished from what and by whom. One reason this idea has endured is that it does not depend on a single speculative framework. It emerges in loop quantum gravity in string theory, in quantum information theory, and in semi-classical gravity. These approaches disagree on many details, yet they converge on the central role of information. That convergence is difficult to dismiss as coincidence. There are, of course, unresolved challenges. How information gives rise to time remains an open problem. How classical spacetime emerges from quantum correlations in realistic cosmological settings is still under active study. How to test these ideas directly remains difficult, but the direction is constrained. Any successful theory of quantum gravity must explain why information limits appear everywhere, and why violating them leads to inconsistency. The phrase, information, is the currency of the cosmos, is sometimes used loosely, but its technical meaning is precise. Currency is what allows exchange and accounting. In physics, information allows prediction and comparison. Without it, no measurement can be defined, no law can be tested, and no experiment can be interpreted. At the smallest scales where matter and geometry lose their familiar roles, information remains the unit that cannot be removed. This is why every attempt to probe deeper circles back to it. Not because physicists prefer abstraction, but because information is what remains invariant when other quantities are pushed beyond their domains of validity. It is the last handle we have on reality when everything else becomes unstable. If information is fundamental, and if spacetime and gravity arise from how it is organized, then scale alone is no longer the limiting concern. What comes into focus instead is the origin of the rules themselves. The constraints that determine how information can be arranged, how it is restricted, and how it remains preserved across the universe. In a picture where reality is written in information, the problem is no longer what the smallest scale is, but what fixes the structure that information is allowed to take. Part 9. If we live on a cosmic screen, who, or what, writes the code? The moment physicists realized that the deepest descriptions of the universe no longer rely on what fills space, but on what is written on its boundaries, the meaning of inside and outside quietly collapsed. This realization did not begin as a speculation about artificial worlds or hidden designers. Is less than #0. 5# is greater than. It emerged from hard calculations, from attempts to make gravity and quantum mechanics coexist without contradiction. The holographic principle does not suggest that reality is fake, nor that it is controlled from elsewhere. It suggests something more unsettling and more restrained. The universe may define itself entirely through relationships across boundaries, without any external reference point at all. To understand why this matters, it helps to separate holography from the popular idea of simulation. A simulation implies an external system running rules imposed from the outside. Holography requires no such structure. It does not rely on a programmer, a computer, or a higher dimensional observer watching from beyond. Instead, it proposes an internal equivalence. Everything that happens within a volume can be fully described by information residing on its boundary. The universe does not need to be rendered. It simply obeys constraints. In holographic models, there is no hidden place where the real physics occurs. The boundary description is not more fundamental because it is external, but because it is complete. The bulk description and the boundary description contain the same physical content expressed in different languages. Nothing is added, nothing is removed. The roots of this idea trace back to black hole physics is less than #0. 5 is greater than. When black holes were found to obey thermodynamic laws, their entropy scaled with surface area. That result forced physicists to confront a basic question. If all information about what falls into a black hole is preserved, where is it stored? The calculations pointed relentlessly to the event horizon, not as a material surface, but as a boundary where information is encoded in a precise and finite way. The entropy formula made testable predictions about how black holes radiate and evolve. Stephen Hawking's work showed that black holes emit radiation with a thermal spectrum, leading to gradual evaporation. The information paradox followed directly from these results. If black holes evaporate completely and if quantum mechanics forbids information loss, then information must be preserved somewhere. The horizon became unavoidable. As the mathematics matured, physicists such as Leonard Susskind and Gerard Hooft recognized that this boundary-based accounting might apply far beyond black holes. The holographic principle was proposed not as a claim about visual projection, but as a statement about information capacity. A region of space can be fully described by degrees of freedom, living on its boundary measured in bits per unit area. This framework reached its sharpest form with the discovery of the AD-CFT correspondence. Juan Maldacena demonstrated that a universe with gravity in a higher dimensional curved space could be exactly equivalent to a gravity-free quantum field theory living on its boundary. Every process in the bulk had a counterpart on the surface. Forces, particles, and even black holes were mirrored by interactions among quantum fields. No information was lost in translation. What made this result extraordinary was not its elegance, but its completeness. The boundary theory did not approximate the bulk. It reproduced it exactly. This equivalence has been tested across thousands of calculations, from particle scattering to black hole entropy. While our universe is not described by the same geometry, the lesson was unavoidable. Gravity, spacetime, and locality could emerge from non-gravitational information dynamics. If the universe can be fully described without reference to an interior substance, then what determines the structure of the description itself? If there is no external programmer, no outside frame, then the rules governing the information must be internal, self-consistent and constrained by symmetry and consistency alone. This is where boundaries take on their full significance. A boundary in physics is not merely an edge in space. It is a limit on what can be known, transmitted, or influenced. Event horizons, cosmological horizons, and causal horizons all function this way. They separate regions not by distance, but by accessibility. Information cannot cross them freely. Once information is restricted, structure follows. In an accelerating universe, observers are surrounded by a cosmological horizon. Beyond it, regions recede faster than light relative to the observer, not because they violate relativity, but because space itself expands. This horizon carries entropy. It has a temperature. It behaves like a boundary with information content. These properties are derived from general relativity and quantum field theory, not added by assumption. Observations by NASA and ESA have confirmed the accelerated expansion of the universe through supernova surveys, cosmic microwave background measurements, and large-scale structure mapping. These observations imply the existence of a horizon with finite information capacity. The universe does not allow infinite detail to be stored or accessed by any observer. This constraint removes the need for an external author, is less than #0. 5# is greater than. The rules are not written by something beyond the universe. They are enforced by consistency. Quantum mechanics limits information extraction. Gravity limits information storage. Thermodynamics limits information processing. These limits intersect in a way that defines the structure of spacetime itself. In this framework, the question of who writes the code becomes ill-posed. There is no code in the conventional sense. There is a set of constraints that any consistent description must obey. These constraints are not optional. Violating them leads to paradox, instability, or inconsistency. The universe selects allowable structures by exclusion. This perspective helps clarify why simulation arguments, while logically interesting, are not required by physics. Holography does not suggest that our universe is implemented elsewhere. It suggests that locality and dimensionality are emergent properties of information organization. The universe does not need to be computed. It needs to be self-consistent. One of the most valuable aspects of this view is that it remains grounded in testable physics. Any proposal about holography must reproduce known results in cosmology, particle physics, and gravitational dynamics. It must account for the cosmic microwave background galaxy formation and gravitational lensing. The James Webb Space Telescope provides new constraints by observing early structure formation. Any boundary-based description must align with these data. There is no appeal to unknowable agents or hidden dimensions beyond measurement. The emphasis remains on what can be calculated, constrained, and compared with observation. Holography survives because it continues to pass these tests, not because it offers dramatic imagery. As the idea matures, its implications sharpen rather than soften. Inside and outside lose their absolute meaning. What matters is which information is accessible to which observers and how that information is organized. Space becomes a derived quantity. Distance becomes a measure of correlation. Gravity becomes a response to information flow. This does not make the universe less real. It makes it more tightly defined. The solidity of objects, the persistence of laws, and the reliability of physical processes all arise from these constraints. Stability is not imposed from above. It emerges from the limited ways information can be arranged, without contradiction. If the universe is fully specified by informational boundaries, and if those boundaries govern everything that can exist and evolve, then the remaining problem is no longer the search for an external author. It is the question of coherence is less than #0. 5# is greater than how such a system maintains stability, continuity, and internal consistency across cosmic time. That unresolved constraint does not point outward but inward toward the mechanisms that allow an informational universe to appear persistent, connected, and physically real at every accessible scale. Part Dis. If space is only an illusion, why does it feel so solid and real? If space is not a fundamental ingredient of the universe, if it is not something that exists on its own, but instead emerges from deeper rules, then the most unsettling fact is not that space might be an illusion, but that it behaves with such extraordinary reliability. Every experiment, every observation, every technology we build assumes that space is stable, distances can be measured, objects remain where they are expected to be, forces weaken predictably with separation. From laboratory scales to cosmic distances, space behaves as if it were a firm stage on which all physical processes unfold. And yet, modern physics keeps returning to the same conclusion. At the deepest level we can probe, space does not appear as a primary object. It appears as an outcome. This tension lies at the heart of contemporary cosmology. Is less than #0. 5# is greater than. On one hand, general relativity treats space and time as a dynamic structure curved by mass and energy. On the other, quantum theories increasingly describe reality in terms of information, correlations, and constraints, with geometry arising only after those relationships are established. These two views are not in conflict. They describe the same universe from different depths. The solidity of space begins with consistency. Is less than #0. 5# is greater than. Even if space-time emerges from something more fundamental, the rules governing that emergence are remarkably rigid. Once large-scale structure forms, the relationships that define distance and duration become stable across enormous spans of time. Galaxies orbit stars, burn atoms, bind, and chemistry proceeds with dependable regularity. This is not accidental. It reflects the fact that only certain informational arrangements can persist without collapsing into instability. Evidence for this stability appears everywhere in observational astronomy. Measurements of gravitational lensing show that space-time curvature behaves exactly as predicted by general relativity, even across billions of light-years. The bending of light around galaxy clusters follows precise patterns. If space were loosely defined or inconsistently emergent, such coherence would be impossible. Instead, geometry behaves as a macroscopic law. Cosmic expansion provides another example. Observations from NASA and ESA show that space itself expands at a rate governed by dark energy. This expansion does not tear atoms apart or disrupt local structures, because the rules governing emergent space preserve local consistency. Space can grow on cosmic scales while remaining effectively rigid on smaller ones. This separation of scales is not assumed, it is measured. Xiaoyu Jinghao Ling, 5# is greater than tiny temperature variations, mapped with high precision, revealed that the geometry of space has remained remarkably uniform since the early universe. These patterns could only survive if the underlying structure of space-time evolved smoothly and predictably. Any emergent description must account for this continuity. The data leave little room for improvisation. Xiaoyu Jinghao Ling, 5# is greater than. By observing galaxies forming within the first few 100 million years after the Big Bang, JWST confirms that large-scale structure followed well-defined gravitational rules from very early times. Even if space-time emerged from quantum information, that emergence must have locked into a stable regime quickly. Otherwise, the observed universe could not exist in its present form. This is why the term illusion requires careful handling. Is less than #0. 5# is greater than an. Illusion in physics does not mean something unreal or deceptive. It means something derivative. Temperature, for example, is not a fundamental property of individual particles. It emerges from collective motion. Yet temperature is measurable, predictable, and indispensable. Space may belong to the same category. It is not fundamental, but it is real in every operational sense that matters. The human experience of solidity arises from this operational reality. Is less than #0. 5# is greater than objects. Resist compression because electromagnetic forces act over stable distances. Surfaces feel firm because atomic structures maintain fixed separations. Motion feels continuous because space-time geometry varies smoothly at human scales. None of these experiences require space to be fundamental. They require space to be consistent. From a physical standpoint, consistency is far more important than origin, is less than #0. 5# is greater than. Whether space-time arises from quantum entanglement, holographic boundaries, or another yet undiscovered mechanism, once it emerges, it must obey strict constraints. Violating those constraints would prevent stable matter, long-lived stars, or coherent biological processes. The universe we observe is not just allowed by these rules, it is shaped by them. Xiaoyu Jinghao Lin, 5# is greater than. When Isaac Newton described space as absolute, his framework worked because it captured consistent relationships between motion and force. When Einstein replaced absolute space with spacetime geometry, the predictions improved not because space became more real, but because the description became more accurate. Each refinement stripped away assumptions while preserving empirical reliability. Modern approaches continue this progression, is less than #0. 5# is greater than. By treating spacetime as emergent, physicists are not discarding reality. They are refining the language used to describe it. Just as thermodynamics emerged from statistical mechanics without losing predictive power, spacetime may emerge from informational laws without losing its physical authority. One of the strongest arguments for this view comes from universality. The same space-time rules apply everywhere we look. From the orbit of the Moon to the motion of galaxies, geometry behaves identically. This universality is difficult to reconcile with ad hoc constructions. It strongly suggests that space-time emerges from simple global principles rather than local improvisation. Information-based models offer such principles. They impose limits on how much can be known, stored, and transmitted. These limits naturally give rise to horizons, distances, and causal structure. Once these features appear, they define a stable arena for physical law. Space feels solid because it is the large-scale manifestation of deep constraints that do not fluctuate at human scales. There is also an important practical consequence. Physics does not require us to experience the fundamental layer directly. We interact with effective laws. These laws are not approximations in daily life. They are exact within their domain. The emergent nature of space does not weaken its reliability any more than the atomic nature of matter weakens the solidity of a table. This perspective dissolves a common misconception. Discovering that space is emergent does not make existence fragile. It explains why it is robust. Only certain emergent structures are stable. Those structures enforce regularity. Regularity allows complexity. Complexity allows stars, planets, chemistry, and eventually life. Carl Sagan often emphasized that understanding our place in the universe does not diminish us. It enlarges context. In this case, the lesson is technical rather than poetic. The universe is not held together by intuition. It is held together by consistency. Laws that emerge must remain compatible across scales, or they disappear. As cosmology advances, this realization becomes more concrete. The task ahead is not to decide whether space is real or illusory. It is to understand how stable geometry emerges from deeper rules, and why those rules permit exactly the kind of universe we observe. This is not a speculative question. It is constrained by data, by observation, and by mathematical consistency. What remains remarkable is that these constraints allow anything at all. The same rules that limit information, restrict curvature, and cap energy density also permit long-lived stars and vast cosmic structures. Space feels solid because it is the macroscopic expression of rules that do not bend easily. And so the journey settles here. whether space-time is fundamental or emergent, whether dimensions arise from information or geometry stands on its own. The universe remains governed by laws that hold steady across time. Those laws are what make observation possible, what allow memory, measurement, and understanding. Thank you for spending this long exploration with me, following these ideas from black holes to information, from boundaries to the space you inhabit every day. If this time has brought even a small sense of clarity or calm, I am grateful you shared it here. Wherever you are listening, and whatever hour has carried you to this moment, I wish you a peaceful rest and a very good night. Good night.